The MatSim dataset focuses on visual recognition of any material in any conditions using one or a few examples. Recognition of materials and their states is essential for understanding the world, from determining whether food is cooked, metal is rusted, or a chemical reaction has occurred. Previous studies on image recognition for materials have focused on material classification and property prediction for a given set of classes like metal and plastic, or liquids and solids. The limitation of these approaches is that they can only work on the classes and properties they were trained on. The MatSim dataset aims to enable one-shot recognition of any material and its state, without being limited to classes or settings used for training. The data consists of highly diverse synthetic images for training and a natural image benchmark for testing. Our hypothesis is that training a net to identify the same material texture on different objects and environments will enable it to recognize material types and states in general. The main assumption is that a large and diverse enough training set will allow the net to learn a strong representation of the material appearance. Scenes in the dataset were generated by combining large-scale CGI repositories for objects, materials, and backgrounds. With dozens of thousands of PBR materials and objects and hundreds of HDRI backgrounds and illuminations, we prepare a CGI scene by first loading a random object. The object's original material is replaced with a random material. We then load a random HDRI panoramic image and set it as the background. In addition, we add a few random objects for background and shadows. Finally, we render the image and the mask of the objects. The synthetic dataset is composed of sets. Each set contains two materials and their mixtures. Each material appears in different scenes on different objects, environments, and mixtures. An example set appears in the picture. Each column contains images of the exact same material, but on different objects and scenes. For each set, we pick two random materials, A and B. To simulate mixtures, we gradually transformed from material A to material B. In the image, the rightmost column is pure material B, while the leftmost column is pure material A. The middle column is an equal mixture of A and B. All images of the same column contain the exact same materials and mixture ratio. We also create scenes where the materials appear inside randomly generated transparent containers to simulate fields like labs, kitchens, and liquid handling. Training a net using the dataset can be done using a Siamese net approach similar to methods like CLIP and SimCLAR. Basically, we pass the image and the mask of the material region through the net to predict a descriptor vector. The cosine similarity between two such descriptor vectors is the similarity between the materials they represent. For training, we picked 3 images from the same set. One image was considered an anchor. From the 2 remaining images, the image with the material more similar to the anchor was picked as positive. The remaining image is set as negative. We train the net using a standard cross-entropy approach to predict that the anchor material is more similar to the positive example than to the negative. To evaluate the ability of the net to identify materials using one example, we present a new few-shot benchmark containing natural images of materials in a wide range of real-world scenes, from cooking and chemistry to rocks and construction. For each material, we pick a few states or subtypes. For each material state, we take at least 2 unique images with different objects and environments, forcing the net to use only the material type for recognition. We then test the ability of the net, given an image, to retrieve images of the same material type from all the images in the benchmark. We use the benchmark to evaluate the net trained on the MatSim dataset, as well as a pre-trained CLIP model. While both achieve good results, the MatSim-trained net significantly outperformed the best available CLIP model. We also test the net on standard materials datasets like DMS and Open Surface by testing its ability to match materials of the same class. The MatSim-trained net again achieves good accuracy, suggesting it learned to generalize beyond its core task.